Yeah, first of all, big thanks, Christian, for organizing this webinar. It's always super interesting. Today, I will give you a short summary of my PhD project that I finished in Canada. I have done it at University Laval, and my supervisor was Celine Van Eekhout. And yes, my title is a little bit long. It's a development of synergies between pyrolysis and anaerobic digester based on micropollutant distribution during biosolid pyrolysis. And yeah, massive title. Let's start with the motivation and problem statement, and then you have an idea where it's going. So motivation and problem statement. So when I started my PhD, the general problem is like in US, we had 4.5 million metric tons of sewage sludge or biosolid produced in US, and 43 is going on land, 42 is going on landfills, and 14 is going in incineration. In Europe, the numbers are a little bit different. However, biosolids are also applied on the field. And when we are applying these biosolids on the field, we are facing some problems that is called micropollutants. And particularly, I'm talking here about heavy metals, dioxin, furans, polyamide components, PCBs, and recently PFAS. I think everybody heard about them. PFAS are high stable components and toxic, and they're so toxic that the government of Maine were a little bit afraid and decided that they don't allow any more biosolids on the field. Okay, we are generating biosolids every day, so we have to find a solution. So main solution was to send biosolids to Canada. Okay, I think it's not a solution. We need alternative technology for reusing sewage sludge. And this technology should be reduce the amount of sewage sludge, should be cheap, recover nutrients, remove ideally micropollutants, and generate renewable energy. And one of these technologies is the pyrolysis. I'm not explaining what a pyrolysis process is. Just shortly, we are generating a solid fraction, the biochar, the aqueous pyrolysis liquid and pyrolysis oil, and a gas fraction. And which brings me now to the problem statement, because as the sun already says, the governments are, at least in Europe, are still really concerned about possible risks because we're starting with a polluted starting material, and the data which are available are still not enough for the European Commission to prove that the biochar out of sewage sludge is safe to apply as a soil amendment. So that is the first problem. And the second challenge what we are facing is like, where micropollutant transferred during pyrolysis? Are they going in another phase, or are they destroyed? And that brings me to the objective of my research project. So the first objective was to determine strategy to obtain a clean biochar. And I couldn't change the starting material. So the starting material is the same. So it's bio solids. However, what I can change is the process parameters and the process. So I can control the process differently to generate a clean biochar. And as soon as I achieved that, the next question was like, or objective was to verify where this kind of micropollutants are transferred. So, and when I have this result, I can give suggestions where to use this kind of end products. And there I'm coming also back to the title, combination of an anaerobic digester and pyrolysis. What kind of method I used? You see here the pilot plant installed at Aquinova in Canada. They give me the possibility to run all my tests with this plant. It's around 3 to 4 meters. And you also see at these pipes, you can add a carry gas. So it is important, as I will share later some results where I added carry gas during the pyrolysis process and also in the cooling process. We are adding biosolids here as they're running through the pyrolysis process. We have a condenser and a thermal oxidizer. What kind of process parameters I used? Or tried to simulate a two-stage pyrolysis process, meaning I added biosolids at 350 degrees in the pyrolysis process, collect the biochar, and then re-edit the biochar at 650 degree and ran it again for 15 minutes. As samples, I collected biosolids to see what kind of micropollutants I have inside, collected the biochar at 350 and 650 and both liquid fractions. Okay, what micropollutants I considered? I take the European biochar certificate as an orientation. I added, on my analyzation, I added polyaromatic components, BCBs, dioxin, furans, heavy metals, and based on the recent topic, PFAS also. And now, it's set it. Now I'm directly jump to one of the results. First question is the determination of strategies for obtaining a clean biochar. So the first question was like, what is inside of my biosolids? And here you can see a huge different kind of amount of heavy metals. You can see a high amount of different PFASs and some dioxin and furans. We didn't detect any polyaromatic components and PCBs. And now, when we are adding this biochar now to pyrolysis process, we are actually generating polyaromatic components. And the good message is here actually at 350 degree, we have like around 1,500 nanograms per gram. However, by increasing the temperature to 650 degree, we are significantly reducing the polyaromatic concentration. For heavy metals, we see the opposite trend. We have an up concentration, that's not new, as organic components are decomposing. However, heavy metals are staying in the biochar. For PFAS and dioxin furans, we see the same trend for both. We see a decrease of concentration and also a decrease of the components in the biochar. And so the message here, by increase of the temperature, we are reducing the polyaromatic concentration, PFAS, dioxin, and furan concentration. However, we are increasing the heavy metal concentration. Okay. I mentioned already the carrier gas supply, and this idea was coming up as I was seeing some studies which were showing CO2 supply during the pyrolysis process have benefits for the biochar properties. It is increasing the surface area, the total pore volume. It has benefits for the Synergies, and also is reducing the tar formation. However, by adding CO2 in this pyrolysis process, we have no idea how it impacts the micropollutant concentration, which brings me back to the plan where we run again some tests. And I added carrier gas, I added CO2 in the pyrolysis process. It was 0.4 liters per minute. And here you can see a comparison between no carrier gas supply in the pyrolysis process with carrier gas supply in the pyrolysis process, and at 350 degree. So for heavy metals, we don't see any impact. For PFAS, it's interesting. We see increase in the removal efficiency. At the beginning, we have here 4 different kind of PFAS components, and we are reducing it to only 1 PFAS component. For dioxin, we see no impact for furans. We see a slight increase. However, I want to mention that we are working in a really, really low concentration in general. So as a message, what I want to share here is CO2 supply in the pyrolysis process has a benefit for the PFAS concentration. It's reducing. It's slightly increasing the furan concentration and doesn't have any impact on heavy metal and dioxin. Okay, the pyrolysis process I take consider it, but now I was like wondering, does it have also an impact when I'm adding CO2 in the cooling process? This idea is coming up because the presence of oxygen is actually increasing the formation of pollutants, and biochar is a high absorber. So when the biochar is coming out of the pyrolysis process, I want to ensure that oxygen, first of all, is not present during the cooling process, and furthermore, maybe micropollutants are evaporating during the cooling process. So I want to be sure that this absorption is not taking place, because these micropollutants are flushed out. So here you can see, so what I have done is I compare no gas supply intercooling process and CO2 supply intercooling process. It's always 0.4 liters per minute. And for heavy metals at 350 degree, no impact. However, now it's getting interesting. At 650 degree, we have a reduction of heavy metals, and it's actually only copper. But this is interesting for later on for the regulation, for the EBC regulation. For PFAS, at 650 degrees, the values are almost, they're equal. The removal efficiency is equal. So for dioxin and furans, here we see definitely a positive trend when we are adding CO2 also in the cooling process. So coming back, dioxin and furans are formed when oxygen is present. So adding CO2 has a benefit in the cooling process. So coming to the conclusion, CO2 supply is reducing dioxins, furans, has also a positive impact on heavy metals and doesn't have any impact on PFAS. So far so good. Strategies are found. However, do we now fulfill the EBC guidelines? So here you can see the EBC guidelines, and I will point directly out the biochar at 650 by adding CO2 into pyrolysis process and then cooling process. And yes, we fulfill, so we were below the detection limit for polyaromatic components. Dioxin and furans was also really, really low, and PCBs was not detected, and PFAS was also really, really low. So we are working here in nanograms per gram. Interesting here, cadmium. With cadmium, we are fulfilling the EBC ACO regulation actually. And also interesting, we were able to reduce the copper concentration. However, we are not fulfilling the EBC guidelines in copper and nickel. Okay, now biochar is somehow clear. What's happening with actually the micropollutants? So we were focusing on the biochar, but we are also generating two liquid fraction and the gas fraction. So I wanted to analyze the distribution of micropollutants. And before I'm showing the results, directly on the beginning, I was unfortunately not able to analyze the gas fraction because the analyzation is really, really complicated and really, really expensive. So I can only show you results about the distribution of the biochar, APL, and the oil fraction, and can give you an assumption that a percentage is going maybe in the gas fraction or decomposed, we don't know. So for PFAS, we can actually see that when we are considering 100% of the PFAS which are going in, we are distributing around 23 into biochar, a little bit is going into APL and the oil. For polyaromatic components, there are almost exclusively, or actually exclusively, landing up in the oil fraction. For dioxin and furans, they were landing mainly up in biochar and in the oil fraction. And finally, heavy metals are mainly landing up in as a biochar. So coming to the conclusion, so we have heavy metals, PFAS, and dioxin and the biochar at 350 degrees. That is supporting the suggestion to re-add the biochar again at the second stage at 650 degrees. Because we are able to reduce the PFAS and dioxin and furan concentration. For APL, we detected some PFAS. For the oil, we detected actually everything. And the gas, we are assuming that there are some PFAS inside, as the PFAS are really stable. And we are assuming also dioxin and furans. However, I didn't measure it, so studies have to follow. Okay, based on these results, so we have an idea what kind of micropollutants are in this end product. What are we going to do? So oil fraction is first of all really a really smelly component, and we have different kind of micropollutants. So my idea was, okay, let's burn it and see what kind of heating value we are achieving. And the heating value is actually really high. So it's around 28 and 34 megajoule per kilogram. Comparing it to ethanol, it's around 30 megajoule per kilogram. So the heating value is high, which is good. The second point, it was the APL fraction. So the APL fraction, what are we going to do with that? So I analyzed it and determined a high COD value. High COD value meaning maybe it's biochar adjustable. So I ran biochemical methane potential tests to determine if my component is digestible. And thereby I was co-digesting the APL fraction, which was generating with no gas supply in the pyrolysis process and with CO2 supply in the pyrolysis process. So I wanted to analyze if my process conditions I selected during the pyrolysis has any impact on the digestibility. And that is how it looks like in the laboratory. And my results are like that. So on the beginning, I have an incubation of around 40 to 42 days. However, after this 42 days, I produced significantly a biogas. So I achieved actually a biogas production about 423 milliliters per gram based on BS, which is high. And this results, and furthermore, it's also showing that the process conditions in the pyrolysis process by adding no carry gas supply or CO2 supply doesn't have any impact. So these results are showing that the APL is digestible, that carry gas supply doesn't have any impact. However, we have a lag phase of around 40 days, suggesting we need a co-digestion or a pre-treatment step. And with this result, now I'm coming back to my title actually, also like how to combine an anaerobic digestion and a pyrolysis process. So I was like coming up with this idea to use the CO2 from after upgrading the biogas. So we can use the CO2 in the pyrolysis process, which has a benefit for the biochar and the properties. And furthermore, also is reducing the micropollutants. Furthermore, we can use the APL fraction of the pyrolysis process to re-add it in the anaerobic digester. That is increasing the anaerobic, the biogas production. And furthermore, we can use the oil and the gas to send it to thermal oxidizer to use the heat for a drying process. The biochar also, I didn't mention it, we can add it in the anaerobic digester. Why this idea is coming up? Biochar is porous, meaning we have a higher surface. When we're adding it in the anaerobic digester, we have a higher surface area, more bacteria, higher gas production, which is already shown in other studies. So that brings me to the conclusion. So the first objective was to determine possibilities to generate a clean biochar. So first, message I want to share or give you is high temperature is reducing organic micropollutants. Second of all, CO2 supply is a benefit for the biochar properties, and also has a reduction in PFAS, for example. Carry gas supply in the cooling process is significantly and really important to ensure that we have a low micropollutant concentration in biochar, and we will fulfill the guidelines with the exception of copper and nickel. Objective 2, polyaromatic components are landing up in the oil fraction, PFAS in the biochar, APL on oil, dioxin furans in the biochar, oil and heavy metals in the biochar. This tests were done at 350°, supporting to add the biochar again in the second pyrolysis stage to reduce PFAS and dioxin and furan concentration. And finally, I show you possibilities to use or combine an anaerobic digester with the pyrolysis process based on the properties. And as a future perspective, Like by adding CO2 into pyrolysis process, it's really interesting as we like as a future perspective, we should make a CO2 balance around it and see if we are able to reduce the CO2, the total CO2, which could be interesting for carbon credits. Furthermore, into future analyzations, we need results for micropollutants into syngas and pyrolysis oil after combustion, after we are sending it to the thermal oxidizer, to see what kind of treatment steps are needed. And finally, the APL fraction, we have to run semi-continuously anaerobic digester test and also see how possibilities to reduce the inhibition of the APL phase on the beginning. And yeah, that's it. And I want to thank also my team, particularly my supervisor and also my team members, Hamid, Amal, and Edgar. And looking forward to an interesting discussion.
Thank you very much, Felicitas. Very interesting, especially because I also worked with sewage sludge. You got a question from John in the chat. In what form does the fluorine report from the PFAS, for example?
Sorry, I don't see the chat.
It up. In what form does the fluorine report from the PFAS? So in what form did you analyze the PFAS?
Oh, okay. The PFAS, I was sending, so I selected different kind of PFAS and I was just sending the biochar directly to olefins. So I was like determining exactly 24 different kind of PFAS. Is this? Yeah. So in the solid fraction, in the solid and two liquid fraction.
Yeah, I also had a question, not fluorine, but so you showed, which I found really interesting. You showed that the cadmium was going down quite a lot when you use CO2 as a carrier gas. Do you know where the cadmium ended up, or do you have an idea what happened there? Because it seems a bit counterintuitive.
Yeah, it's kind of continuous. The point is like CO2 is not like nitrogen. CO2, particularly at higher temperature, is reactive and can go in the reaction. So there's an assumption. So cadmium is restaying as cadmium carbonate. So there's a possibility that CO2 is decomposed. That there's a cadmium carbonate decomposition, and cadmium is landing up in the gas phase and it's going in the gas phase.
Okay, so most likely gas phase.
Yes, most likely gas phase, as I didn't detect it into liquid fraction, so somewhere it has to go.
Yeah,
so there.
Yeah, no. Joao Santos was asking, what percentage of biochar did you get after the second stage? What biochar yield compared to from the biomass?
Okay. Okay, that's a the exact numbers I don't know anymore, unfortunately. I have to look it up. I will answer. I don't want to say any wrong numbers, so I will when he can text me per email or send me his email, I will send him the exact number. I think it was 60%, but I don't want to give an exact number. But when you text me into chat, I will directly write the email.
Problem once you're done, you forget.
Yeah.
So you got a follow-up question from John about the fluorine. What becomes of the fluorine? Does it remain in the form of PFAS after 650 degrees, or where do you expect it to degrade or be emitted?
Okay, good question. So both. There's an assumption, as I didn't measure it, but some results or other publications show there is a decomposition. It's definitely depending which kind of PFAS we have. Some PFAS are more stable, some are not, are decomposing. Results are showing from another researcher that we have a decomposition of PFAS, but in smaller components. We have probably both.
And I guess there's no definite answer yet. Or
No,
just
there's no definitely answer. So that is also, as I pointed out at the Outlook, said we have definitely to run tests around the thermal oxidizer to see, okay, what kind of components we are standing in the thermal oxidizer and what kind of components we are getting out after 1200 degree when we are decomposing it.
and maybe one more question from myself. So have you checked what to do with the biochar in your case? What would the end application be, as a soil amendment or better,
So
I don't know, or
sorry, the project was focusing on to use biochar as a soil amendment. However, you can use the biochar also differently. I think also an interesting perspective is actually first to figure out where to use the biochar. Maybe we can use it as an absorber for wastewater treatment plants. Maybe we can see it as micropollutant removal and as a force and like for cleaning step, or adding it in an anaerobic digester. And based on the areas where we want to add the biochar, we can adapt the process parameters actually. So it's also interesting to adapt the process by seeing, okay, we want to use this kind of biochar, sets the market where we want to use it. Let's change the process parameters and see if we are fulfilling this kind of properties what we need. So I think we can see, we can start to think a little bit different maybe also.
and are there
And
any?
construction, yes, somebody said also construction. Construction is also a big part. There's one important factor, constant properties actually. When customizer want to use it in the construction, properties have to be constant. So there was one conference where they try to where they mentioned that's a big challenge actually to say, okay, what kind of properties do we have constantly? So I think there's definitely research needed.